50 years ago, NASA launched two small spacecraft with one simple mission: explore the outer planets. Today, Voyager 1 and 2 have gone far beyond anything ever sent by humanity, and along the way, they completely transformed what we know about the solar system. Opening sequence: two probes that never came back. In 1977, two spacecraft left Earth with a plan that sounded simple on paper, but was built on timing that would not come again for more than a century. These two machines were named Voyager 1 and Voyager 2, and they were built to do something that had never been done before: fly past the giant outer planets of the solar system using a rare alignment that lined up Jupiter, Saturn, Uranus, and Neptune in a way that allowed one spacecraft to use the gravity of one planet to swing into the next. This alignment does not stay available, and once it passes, the same route cannot be repeated in any human lifetime. So the entire mission depended on launching at the exact moment when nature itself briefly arranged a shortcut across the solar system. The goal was not to leave the solar system. That part was not even part of the original mission plan. The goal was to reach Jupiter, use it as a gravity source, then move on to Saturn, and for Voyager 2, continue further to Uranus and Neptune. Voyager 1 was aimed on a faster path that would focus on Saturn and its largest moon, Titan. Everything about the mission was designed around close flybys, quick data collection, and then silence, after a few years when the power systems would run low. Engineers at the time did not build Voyager expecting it to survive long journeys beyond the outer planets, because nothing like that had ever been tested or even seriously planned. The spacecraft themselves were built under extreme limits that feel almost unreal compared to modern technology. Each Voyager carried a computer system with around 68 kilobytes of memory, which is less than what a simple text file can hold today. The instructions were stored in systems that used long-dead technology by modern standards, including magnetic tape systems that worked more like early recording devices than modern digital storage. There were no powerful processors, no onboard intelligence, and no ability to react to unknown situations in a flexible way. Every major action had to be written in advance and sent as a command from Earth. The communication system was another serious limitation. The spacecraft could only send back weak radio signals, and as they moved farther away, those signals became extremely faint. Even at the start of the mission, engineers knew that every message would take time to travel, and that time would grow longer every day. There was no real-time control. Every instruction sent from Earth would take minutes, then hours, then eventually days to reach the spacecraft depending on distance. The spacecraft were not being flown in the normal sense. They were being guided slowly through signals that travelled at the speed of light but still felt painfully delayed because of the distances involved. At launch, the expectation was very direct. Voyager 1 and Voyager 2 were expected to last around 5 years, maybe a little more, if systems held up well. After that, the instruments would begin to fail, the power would drop, and the spacecraft would drift into silence. No one designed them to become long-term explorers. They were not built to survive decades. They were built to complete a specific route through the outer planets and then fade out as their power sources weakened. The mission path was carefully planned. Voyager 1 would travel to Jupiter first, then use Jupiter's gravity to accelerate towards Saturn, where it would take a close look at Titan before leaving the planetary system entirely. Voyager 2 had a longer and more complex route. It would visit Jupiter and Saturn like Voyager 1, but it would then continue further, using additional gravity assists to reach Uranus and Neptune, making it the only spacecraft ever sent to those planets up close. Everything depended on gravity assists, a method that turns planets into moving engines without burning fuel. Instead of carrying enough fuel to travel across billions of kilometers, Voyager used the motion and gravity of each planet to gain speed. When the spacecraft approached a planet, it would fall into the planet's gravitational pull and gain velocity as it moved closer. Then, as it swung around the planet and escaped its gravity, It would carry away a small part of that planet's orbital energy. The planet would lose an extremely tiny amount of motion that cannot be measured in any practical sense, while the spacecraft would gain enough speed to continue to the next target. This process is not a push in the traditional sense. It is closer to a timed swing. The spacecraft approaches at a precise angle, enters the planet's gravity field, and uses the movement of the planet itself to gain energy. If the timing is wrong, the spacecraft misses the entire benefit. If it is correct, the spacecraft leaves the planet moving significantly faster than it arrived, without using extra fuel. This method is what made the Voyager mission possible in the first place, because without gravity assists, no rocket in the 1970s could have carried enough fuel to reach all the outer planets in a single mission. The launch system that carried Voyager into space was the Titan IIIe Centaur rocket, a multi-stage system designed to push spacecraft beyond Earth's gravity well and into deep space trajectories. The launch had to be precise, not just in direction, but in timing down to small windows, because the entire mission depended on meeting planets at exact points in their orbit years later. A small delay or error at launch would have completely changed the path and removed the ability to visit multiple planets. Once the spacecraft left Earth, the journey became a slow expansion into a region where everything changed. The Sun's influence still dominated, but distance began to stretch every signal, every measurement, and every correction sent from Earth. The spacecraft were moving into a region where sunlight becomes weaker, where planetary bodies become sparse, and where navigation depends entirely on careful tracking from Earth-based systems. The Deep Space Network became the central connection between Earth and the Voyagers. This network of large radio antennas spread across different parts of the world was responsible for catching the extremely weak signals sent by the spacecraft. These signals were not strong enough to stand on their own. They required massive receivers, precise calibration, and constant tracking as Earth rotated. Even a small misalignment in the antenna direction could cause the signal to be lost completely. As distance increased, communication delays became a major part of every operation. A command sent to Voyager would take hours to arrive, and the response would take hours to return. This meant that every decision had to be planned far in advance. There was no quick correction if something unexpected happened. Engineers had to predict problems before they occurred and prepare responses that might only be needed many hours or even days later. Voyager 1 and Voyager 2 began to separate in their paths as they moved through space. Voyager 1 took a faster trajectory after its encounter with Saturn, especially after its close pass with Titan, which redirected it upward out of the plane of the solar system. This change made it the fastest and most distant human-made object in history. Voyager 2 followed a longer path that kept it in the planetary plane longer, allowing it to continue toward Uranus and Neptune, something no other spacecraft has done. The difference in their trajectories was not accidental. It was built into the mission design. Voyager 1 was aimed for speed and early exit after its Saturn encounter, while Voyager 2 was designed for extended planetary exploration. This created two very different journeys from the same launch event, with one spacecraft becoming the fastest path outward and the other becoming the only visitor to the outermost planets. As the spacecraft moved farther away, the original mission plan began to shift without any formal change in intention. There was no single moment when the mission was redefined. Instead, the spacecraft simply kept working beyond expectations. Systems that were not expected to survive continued operating. Instruments that were meant to shut down after a few years kept sending data. Power systems weakened but did not fail completely. Communication became slower but remained possible. The most striking part of this early phase of the Voyager mission was not just what the spacecraft did, but how long they kept doing it. What began as a short planetary mission slowly turned into something else, without anyone redesigning it. The spacecraft continued moving outward, continuing to send data, continuing to respond to commands, and continuing to function in an environment that grows harsher with distance. As they left the region of the giant planets behind, They entered a space environment that had never been measured directly before. The solar system did not end at a visible boundary. It stretched outward into a region filled with solar winding, magnetic fields, and particles that slowly thin out with distance. The Voyagers were now moving into this region without a clear map, carrying instruments that would begin to reveal what exists beyond the planets. The mission that started with a strict 5-year expectation had already moved beyond its original limits. The spacecraft were no longer just planetary explorers. They were becoming long-range observers of space itself, continuing outward into regions where no spacecraft had been designed to survive for long, yet still transmitting, still moving, and still collecting data from a part of space that had never been measured before. Jupiter System discoveries, Voyager 1 and Voyager 2. When Voyager 1 and Voyager 2 reached Jupiter in 1979 and 1980, the spacecraft were not just passing by another planet. They were entering a system that behaved in ways no one had ever seen directly up close before. Because Jupiter is not a quiet planet sitting in space, it is a massive world with storms that cover its entire surface, a magnetic field that stretches far beyond what most planets produce, and a group of moons that act almost like a second planetary system living around it. And every instrument on the Voyagers began recording details that changed what was known about how large planets and their moons actually work in real space conditions. The first shock came from Io, a small moon that at first looked like just another crater-covered rock. But as Voyager moved closer, the images showed something completely different. Because Io was not shaped by slow impacts over time, it was being reshaped right in front of the spacecraft's cameras. And this is where the first clear signs of active volcanoes outside Earth were seen. Not as distant guesses or indirect hints, but as real plumes rising above the surface, shooting material high into space, forming thin arcs that could be seen against the black background of space. And this changed the way scientists understood how small moons behave when they are placed close to a massive planet like Jupiter. Io's surface was covered with bright yellows, reds, and whites, and these colours were not random. They came from sulfur and sulfur compounds spread across the surface, and what made this even more striking was that there were almost no impact craters visible, which meant the surface was being renewed constantly, faster than meteor impacts could leave marks, and Voyager data showed that this constant renewal was happening because Io was being pulled and stretched by Jupiter's gravity, and also by the gravitational pull of nearby moons, especially Europa and Ganymede. And this repeated pulling created internal heat through friction deep inside the moon, a process known as tidal heating, where the inside of a body becomes warm, not from sunlight, but from constant flexing under gravity. As Io moved around Jupiter, its shape was being slightly changed again and again. Not enough for the human eye to notice directly, but enough to generate extreme heat inside its rocky structure. And that heat had nowhere easy to escape except through volcanic activity. So molten material found paths to the surface and erupted outwards, forming plumes that Voyager captured as tall, narrow jets rising above the edge of the moon. And these eruptions were not occasional events. They were part of an ongoing process that made Io the most volcanically active object in the entire solar system, far more active than Earth when measured by volume and frequency of eruptions. The Voyager instruments also detected how fast the material was moving and how far it was being thrown into space. And some of the plumes reached heights that were higher than the diameter of Io itself when compared to scale. And this meant that material was not just staying on the surface, but was being recycled between the moon and space around Jupiter, creating a thin cloud of particles that spread along Io's orbit and contributed to Jupiter's surrounding environment in ways that were only beginning to be understood at the time of the flyby. As Voyager moved further through the Jovian system, attention shifted to Europa, a moon that appeared smoother and brighter than most other moons in the solar system, and what stood out immediately in the images were long, dark lines crossing the surface in different directions, forming patterns that looked like cracks frozen in place. And these cracks were not random surface features. They formed a global network that suggested the surface was moving and shifting beneath a solid outer layer of ice. The smoothness of Europa's surface was a key detail because there were very few large impact craters, which suggested that whatever was shaping the surface was also removing old marks, replacing them with newer material over time. And Voyager images showed that these linear fractures sometimes intersected and sometimes ran parallel for thousands of kilometers, which pointed to a surface that was under stress, being pulled and stretched by forces beneath it. The key process responsible for this activity was again linked to Jupiter's gravity, but in a different way than Io, because Europa's interior was likely made of ice and rock, and as it moved in its orbit, the changing gravitational pull created internal heat that could weaken the ice layer. And under that ice layer, data suggested there could be a layer of liquid water, not visible directly, but inferred from the way the surface behaved and the way the cracks formed and shifted. And this possibility came from the fact that solid ice alone would not produce such organized fracture systems without something beneath it moving or flowing in response to stress. Voyager did not confirm an ocean, but it provided the first strong physical clues that something beneath the surface could be moving in a way that affected the surface above it. And this changed Europa from being a simple icy moon into a world where internal activity had to be considered in order to explain what was being seen. Farther out in the system, Voyager encountered Ganymede, the largest moon in the solar system, and here another unexpected discovery appeared. Because Ganymede was found to have its own magnetic field, which meant it was not just a passive object moving through Jupiter's magnetosphere, but had its own internal magnetic structure, generating a protective field around it, something that had only been clearly confirmed on planets up to that point. The detection of Ganymede's magnetic field came from how charged particles behaved near the moon, because as Voyager passed by, its instruments measured changes in particle direction and intensity, and these changes showed that the moon was influencing the surrounding space environment in a structured way, creating a small region where magnetic lines were shaped by Ganymede itself rather than Jupiter. And this was a major finding because it meant that a moon could generate a magnetic field if it had a liquid or moving conductive layer inside, most likely a metallic core or a conductive ocean layer deep below the surface. Ganymede's surface also showed two distinct types of terrain, one older and heavily cratered, and another younger and smoother. And this suggested that parts of the moon had been resurfaced in the past through internal activity, meaning that even this distant icy world had some form of geological evolution, rather than being completely inactive. While the moons were revealing internal activity and unexpected structures, Jupiter itself was showing a level of atmospheric complexity that was far beyond what had been seen from Earth-based observations, because Voyager images and data revealed a system of storms stacked in layers, moving at different speeds and directions, with the most famous feature being the Great Red Spot, a massive storm system larger than Earth that had been active for centuries. Voyager's close approach allowed detailed study of the structure of this storm, showing that it was not a simple spinning circle of gas, but a highly organized system with internal motion, where winds at the edges moved faster than those closer to the center, and the storm's color variation suggested chemical processes happening within the cloud layers, with different compounds reacting under sunlight and pressure differences in Jupiter's thick hydrogen atmosphere. Beyond the Great Red Spot, Voyager detected smaller storms scattered across the planet, some forming and fading within days, others lasting longer and interacting with nearby systems, and lightning activity was detected deep within the atmosphere, not just as occasional flashes, but as repeated electrical discharges occurring in regions where pressure and temperature conditions allowed clouds of ammonia and water vapor to interact in unstable ways, producing electrical buildup and release. These lightning events were especially important because they confirmed that Jupiter's atmosphere was not just a calm layer of gas, but an active weather system with energy moving through different layers. And the composition of the atmosphere, mainly hydrogen and helium, meant that these storms operated under conditions very different from Earth's weather systems, requiring new models to explain how energy moved and built up across such a large and deep atmosphere. Voyager also revealed details about Jupiter's cloud layers, showing that the atmosphere was structured in bands that ran parallel to the planet's rotation, with alternating light and dark zones where gas moved in different directions at different speeds, creating shear zones that help form and sustain storms. And these banded structures extended across the entire planet, showing that Jupiter's atmosphere was not local in its behaviour, but global in scale. One of the quieter but still important discoveries was the detection of a faint ring system around Jupiter, something that had not been clearly seen before Voyager's close-up imaging because Jupiter's rings are extremely thin and made mostly of dust particles rather than large ice chunks, and these particles were traced back to small inner moons whose surfaces were constantly being hit by micrometeoroids, ejecting dust into space that slowly formed a thin ring structure around the planet. Unlike Saturn's bright and wide rings, Jupiter's rings were dark and narrow, almost invisible, except when viewed from specific angles, and Voyager data showed that these rings were not stable structures in the long term, but were continuously replenished by material from small moons, meaning that the ring system was an ongoing process rather than a fixed feature. The presence of these rings also helped explain how small moons near Jupiter interact with their environment, because they are constantly being bombarded by space debris, and their surfaces act as sources of dust that spreads outward, forming a faint but measurable structure around the planet that can only be seen clearly with close-range observation. As Voyager moved through the Jupiter system, each set of observations connected to the next, showing a system where moons, rings, magnetic fields, and atmospheric activity were all linked through gravity, motion, and energy transfer. And what emerged was not a simple planet with satellites, but a complex system where every part influenced another, from volcanic activity on Io feeding particles into space, to Europa's cracked ice surface hinting at hidden internal motion, to Ganymede, generating its own magnetic field, while Jupiter itself drove everything with its massive gravity and powerful radiation environment. Saturn's system breakthroughs, Voyager 1 and Voyager 2. When Voyager 1 and Voyager 2 moved into the Saturn system, the distance from Earth was already so large that every signal arriving from the spacecraft carried a kind of delay that made real-time control impossible, and at the same time, the light from the Sun was weaker. The space around the planet was darker, and the instruments on board were now dealing with an environment where everything depended on careful timing and slow, steady observation rather than quick reaction. And as Saturn grew larger in the cameras, it was not just another planet appearing in the frame, but a full system that stretched far beyond what could be seen from Earth, with rings that extended outward in thin layers and moons that moved in precise patterns that looked simple at a distance, but became far more complex as Voyager came closer and started recording details that could never be seen from telescopes alone. Saturn itself showed a deep layered atmosphere made mostly of hydrogen and helium, and what stood out immediately in the Voyager data was that the planet was not uniform in appearance, because its surface was divided into soft bands that wrapped around the planet in long horizontal lines, each band moving at different speeds. And these differences in speed created slow-moving shear zones where storms could form and last for long periods of time. And the clouds themselves were not fixed structures, but moving systems that changed shape as they flowed across the planet. And the deeper the instruments looked into the atmosphere, the more the structure appeared to be built in layers, where temperature, pressure, and chemical composition shifted gradually rather than abruptly, creating a vertical structure that worked almost like stacked levels of motion, rather than a single uniform gas layer. As Voyager 1 approached Titan, the largest moon of Saturn, the first thing that became clear was that Titan was not going to show a solid surface in visible light imaging, because even from a close distance, the moon was wrapped in a thick orange haze that completely blocked direct view of the ground. And this haze was not a thin layer sitting at the top of the atmosphere, but a deep and complex system of particles suspended in nitrogen-rich air. And what made this especially important was that Titan was the only known moon in the solar system with a dense atmosphere. And this atmosphere was mostly nitrogen, similar to Earth in its main component, but completely different in behaviour because of temperature and chemistry conditions that shaped everything in a slower and colder way. Voyager instruments measured the composition of Titan's atmosphere and confirmed that nitrogen was dominant, with methane also present in significant amounts. And this combination created chemical reactions driven by sunlight in the upper atmosphere, where ultraviolet radiation broke apart molecules and allowed new compounds to form. And these compounds then created thick organic haze layers that absorbed and scattered light, making the surface invisible to Voyager's cameras. And this meant that instead of seeing surface details, the spacecraft was seeing only the outer structure of a planet-sized atmospheric system that was actively producing complex organic molecules in its upper layers. The importance of Titan was not in what was seen on the surface, because the surface could not be seen at all, but in what the atmosphere revealed about chemical processes happening over long periods of time. Because the data showed that nitrogen and methane interactions were not static. They were continuously driven by energy from the sun, producing layers of haze that built up and shifted over time. And these layers created a system where sunlight, atmospheric chemistry, and particle formation were all linked in a cycle that kept the atmosphere thick and opaque. And this made Titan one of the most chemically active environments in the outer solar system, even though its surface remained hidden behind its atmospheric shield. As Voyager 1 moved past Titan and Saturn, attention shifted to the rings, and this is where one of the most detailed and visually striking parts of the mission unfolded. Because Saturn's rings were not a single flat structure, but a system made of many separate rings, each with its own density, particle distribution and motion. And the spacecraft images showed that these rings were divided into major sections labelled A, B and C, with smaller gaps and divisions inside them that created a layered structure that extended outward from the planet like a wide, thin disk made of countless small particles. What made the rings especially interesting was the way they behaved under Saturn's gravity and the influence of nearby moons, because the ring particles were not fixed in place. They were constantly moving, colliding, and spreading out in thin layers. And Voyager data showed that most of the particles were made of water ice, which meant the rings were extremely reflective in some areas and darker in others, depending on particle size and density. And this variation created patterns that change with distance from the planet, forming bright bands where particles were dense and darker gaps where particles were sparse. One of the most important discoveries in the ring system came from the observation of gaps within the rings, especially narrow empty regions that were not random, but shaped by the gravitational influence of small moons orbiting near or within the ring structure. And these moons acted like guiding objects that cleared paths through the ring material, creating sharp edges and defined boundaries in places where otherwise the particles would have spread evenly. And this interaction between moons and rings showed that the ring system was not separate from the moons, but directly connected to them in a dynamic way, where gravity constantly reshaped both systems at the same time. The structure of the rings also showed wave-like patterns within the particle layers, not waves of water or air, but density waves created by gravitational interactions, where the pull of moons and the rotation of Saturn produced ripples in the distribution of particles. And these ripples moved through the rings like slow disturbances, changing density and brightness as they passed through different regions. And Voyager instruments captured these variations in detail, showing that the rings were not static bands, but moving systems shaped by continuous gravitational interactions. As Voyager continued its path through Saturn's system, it also observed smaller moons embedded within or near the rings, and these moons played a direct role in shaping ring structure by pulling material away or pushing it into specific paths. And this created a balance between accumulation and removal of particles that kept the rings in their current thin and spread out form, meaning that the rings were not permanent solid structures, but ongoing processes that depended on constant replenishment and gravitational shaping to maintain their shape over time. Beyond the rings and Titan, Voyager 1 also passed close to Enceladus, a smaller moon that at first appeared as a bright, smooth object with a very high level of reflectivity compared to most other moons in the system. And this high reflectivity, known as albedo, suggested that the surface was covered in fresh, clean ice that reflected a large portion of sunlight. And this was unusual because most older surfaces in space become darker over time due to dust accumulation and radiation exposure. But Enceladus appeared almost newly resurfaced in many areas. The surface images from Voyager showed relatively few large impact craters, which meant that the surface was either young or being renewed in some way. And while Voyager did not detect direct signs of active geysers or plumes at the time, the smooth and bright appearance of the surface created strong hints that internal processes could be reshaping the outer layer, possibly through heating and resurfacing mechanism beneath the ice. And this made Enceladus stand out as a moon that did not fit the pattern of being geologically inactive, like many other small icy bodies in the outer solar system. As Saturn itself filled more of the Voyager cameras, the planet's atmospheric structure became clearer, and the banded appearance seen from a distance resolved into deeper layers of motion, where clouds at different altitudes moved at different speeds. And this vertical separation created a complex weather system where storms could develop at certain layers and remain stable for long periods of time. And within these layers, Voyager detected large storm systems that appeared as bright and dark regions shifting slowly across the planet's surface. One of the most interesting features in Saturn's atmosphere was the presence of large-scale circulation patterns near the poles, where the motion of gases formed organized structures that rotated around central points. And while Voyager did not fully resolve the most complex polar formations that would be studied in later missions, it did capture early signs of structured atmospheric motion in these regions, showing that even the poles of Saturn were not calm or uniform, but part of a global atmospheric system that extended from equator to pole in continuous motion. The atmosphere also showed evidence of storm activity, driven by internal heat and external solar input, where energy differences created rising and falling gas movements that led to large-scale weather systems forming and dissolving over time. And these storms were not isolated events, but part of a continuous cycle of atmospheric energy transfer, where heat moved through different layers and created visible changes in cloud structure and brightness across the planet. As Voyager moved through the Saturn system, it also measured changes in Saturn's magnetic environment, where charged particles interacted with the planet's magnetic field and created regions of trapped radiation and plasma movement. And this magnetic field extended far beyond the visible planet, influencing ring particles and moon surfaces, and shaping how material moved through space around Saturn, connecting the planet, its rings, and its moons into a single interacting system rather than separate objects. The interaction between the magnetic field and the rings was especially important because charged particles could affect the motion and distribution of small dust grains. And this created subtle changes in ring density and structure that depended not only on gravity, but also on electromagnetic forces, adding another layer of complexity to the system that Voyager was recording in real time. Voyager 2 Extended Mission Uranus Encounter. Voyager 2 reached Uranus in January 1986 after a long journey that stretched across years of silence, weak signals and slow correction commands coming from Earth. And when the spacecraft finally moved into the Uranian system, it entered a region that looked calm at first glance, but behaved in ways that quickly challenged every expectation about how a planet far from the Sun should look and act. Because Uranus did not present itself with obvious storms or bright cloud bands like Jupiter or Saturn's. Instead, it appeared as a pale blue-green sphere, with a soft glow and almost no visible structure at first sight. And this calm appearance created a strange contrast with what the instruments began to record underneath that simple outer look, because the planet was carrying a set of physical conditions that made it completely different from the other giant planets Voyager had already passed. One of the first things that stood out clearly was the tilt of Uranus. Because the planet was not rotating in a way that matched the usual upright spin seen in most planets, instead it was rotated almost on its side with an axial tilt of about 98 degrees, which meant that for long periods during its orbit, one pole would face directly toward the Sun, while the other remained in darkness. And this created a system where seasons were not mild or gradual, but extreme in duration and intensity, stretching for decades at a time. And Voyager data showed that this unusual tilt influenced how heat moved through the atmosphere and how energy from the Sun interacted with the upper layers of gas. Because instead of a balanced distribution of sunlight, different regions of the planet experienced long cycles of illumination and darkness that shaped the atmospheric structure in slow and uneven ways. The spacecraft instruments recorded a planet that did not show strong visible storms at the level of detail seen on Jupiter or Saturn. But this lack of visible activity did not mean that Uranus was inactive, because deeper analysis showed that the atmosphere was layered and structured in ways that were not immediately visible in reflected light, and the methane in the upper atmosphere absorbed red light, giving Uranus its blue-green color, while also hiding deeper atmospheric motions that were only partially revealed through infrared and radio measurements, meaning that much of the planet's internal behavior was hidden beneath a calm surface appearance that could easily be misread without close scientific measurement. As Voyager 2 moved deeper into the Uranian system, attention turned to the moons. And this is where the mission began to reveal one of its most surprising set of discoveries, because the moons of Uranus were not uniform or simple icy bodies. Instead, each one showed a different history written on its surface, and the differences between them suggested that they had experienced different levels of internal activity and external impact over time, with some surfaces appearing heavily cratered and old, while others showed signs of resurfacing and structural change. Miranda was the most striking of these moons, even though it was the smallest of the major Uranian moons visited by Voyager 2, because its surface was broken into extreme geological patterns that did not match any simple formation process, and the spacecraft images showed giant fault cliffs that dropped sharply across the surface, along with regions that looked like they had been rebuilt or rearranged in the past through internal forces that pulled and reshaped the moon's outer layer, creating a patchwork appearance where different sections of the surface seemed to belong to different stages of geological history. And this mix of old and new terrain suggested that Miranda had experienced periods of strong internal activity that reshaped its surface in ways that were still visible at the time of the Voyager flyby. The fault cliffs on Miranda were not small surface cracks, but large vertical drops that created dramatic changes in height across the moon's terrain. And these structures suggested that the interior of Miranda had once been warm enough to allow movement and deformation of its icy crust. And even though the moon is small and should have cooled long ago, the patterns seen by Voyager showed that internal forces had been strong enough at some point to break and reorganize large sections of its surface, leaving behind a structure that looked like different geological pieces had been stitched together over time, without smooth transitions between them. Moving outward from Miranda, Voyager 2 also observed Ariel, a moon that showed a smoother surface in many areas but still carried signs of resurfacing events, where older cratered regions were partially replaced by newer terrain. And this suggested that Ariel had gone through a period of internal activity that had modified its surface more recently than some of the other moons, because crater counts indicated that some areas were relatively young in geological terms, meaning that the surface had been refreshed in ways that erased older impact marks and replaced them with smoother plains. Umbriel, on the other hand, appeared much darker and more heavily cratered, with fewer signs of resurfacing, and its surface reflected less sunlight, suggesting that it had remained relatively unchanged for a long period of time, preserving an older surface that had not been significantly altered by internal processes. And this difference between umbreal and aerial showed that even within the same planetary system, moons could evolve at very different rates depending on internal heat, composition and orbital influences, leading to a wide range of surface conditions across bodies that were otherwise similar in size and composition. Titania and Oberon, the largest moons in the Uranian system, also revealed their own histories through surface patterns, where Titania showed signs of fault systems and possible past tectonic activity that had created long linear features across its surface, while Oberon appeared more heavily cratered and older, preserving impact marks that suggested less resurfacing over time. And together these moons formed a record of different geological timelines within the same system, where each body carried evidence of its own internal and external history, shaped by varying levels of energy and motion. As Voyager 2 passed through these moons and continued deeper into Uranus's environment, the spacecraft also began measuring the planet's magnetic field. And this is where another unexpected feature appeared, because instead of a magnetic field aligned neatly with the planet's rotation axis and centered within the planet, Uranus showed a magnetic field that was both highly tilted and significantly offset from the center, meaning that the magnetic poles were not aligned with the physical poles of the planet, and the magnetic field itself did not originate from the exact center of the planetary body, creating a complex and uneven magnetic structure that shifted in space as the planet rotated. This unusual magnetic configuration meant that the environment around Uranus was not stable in the same way as other giant planets, because the magnetic field interacted with solar wind and charged particles in irregular patterns, creating a constantly changing region of magnetic influence that varied depending on position and rotation. And Voyager instruments recorded how charged particles moved through this region in ways that were less predictable than in the more structured magnetic environments of Jupiter and Saturn, showing that Uranus had a more chaotic interaction between its internal magnetic generator and the space environment around it. The offset of the magnetic field also suggested that the internal structure responsible for generating it was not centered in the same way as Earth or Jupiter, and this pointed toward a region inside the planet where conductive materials were moving in uneven layers, possibly in a shell closer to the outer regions rather than deep in a central core. And this configuration created a magnetic field that appeared to wobble and shift as the planet rotated, producing a space environment that was constantly changing rather than steady. As Voyager 2 continued its flyby, the spacecraft also discovered and imaged the ring system of Uranus, and this was another major surprise, because unlike the bright and wide rings of Saturn, Uranus's rings were extremely dark, narrow, and difficult to detect, consisting of thin bands of material that were not easily visible in reflected sunlight. And these rings were composed mostly of dark particles that reflected very little light, making them almost invisible from Earth-based observation before Voyager's close approach. The ring system consisted of multiple narrow rings separated by gaps, and these rings appeared tightly confined rather than widely spread, suggesting that some form of gravitational influence was keeping the material in narrow paths. And this confinement pointed toward the presence of small moons, or gravitational resonances that acted to hold the rings in place, shaping them into defined structures rather than allowing them to spread evenly into space. Unlike Saturn's rings, which are mostly made of bright water ice that reflects sunlight strongly, Uranus's rings were dark and likely composed of material that had been processed by radiation over long periods of time, causing it to lose reflectivity and become darker. And this difference made the Uranian rings much harder to detect and gave them a very different appearance when compared directly with the more visually striking ring system of Saturn. The narrow nature of these rings also suggested that they were not ancient stable structures, but dynamic systems that required continuous maintenance through collisions, gravitational interactions, and material exchange with nearby moons. Because without such processes, the rings would likely spread out or collapse over time. And Voyager data supported the idea that small moons within or near the rings played a key role in shaping their edges and maintaining their structure through gravitational interactions that acted like boundaries, keeping the material confined to specific paths around the planet. Neptune Encounter, the final planet flyby. Voyager 2 reached Neptune in 1989 after a journey that had already stretched far beyond its original mission length. And by this point, the spacecraft was no longer just passing through a planned route. It was moving through the last major planetary target in the outer solar system, a region where sunlight was extremely weak. Communication delays were stretched to hours, and every instrument on board had already survived years longer than expected, yet still continued to function well enough to return data from a planet that had never been seen up close before. And as Neptune slowly grew from a faint blue point into a full disk inside the spacecraft's camera, what appeared first was not chaos or visible complexity, but a deep, uniform blue color that looked almost calm compared to Jupiter or Saturn. And this calm appearance made the upcoming discoveries even more striking, because what the images initially hid was a level of atmospheric motion that turned out to include the fastest winds recorded anywhere in the solar system. Neptune's atmosphere is made mostly of hydrogen, helium, and methane, and the methane plays a direct role in the planet's color because it absorbs red light and reflects blue light back into space, which is why Neptune appears as a deep blue sphere when viewed from a distance. But Voyager data showed that this color was not just a surface effect, it was connected to the way light interacted with different layers of the atmosphere, where methane concentration and cloud height determined how much light was absorbed or reflected. And beneath this visible layer, the atmosphere was not still at all, but filled with motion that became more extreme as Voyager moved closer and began tracking cloud movements across the planet's surface. The most surprising atmospheric discovery came from the measurement of wind speeds, because Neptune's winds were not just strong, they reached speeds that exceeded anything measured on Jupiter or Saturn, with some cloud systems moving at more than 2,000 kilometers per hour. And these winds were not random gusts, but structured jet streams that flowed around the planet in bands, similar in shape to those seen on other gas giants, but far more intense in speed. And what made this even more unusual was that these winds did not match the expected energy input from sunlight alone, because Neptune is extremely far from the Sun and receives very little solar energy, which meant that the source of this energy had to come from internal processes inside the planet itself, possibly slow heat release from formation or internal atmospheric dynamics that were not yet fully understood at the time of the Voyager flyby. One of the most visible features recorded by Voyager was the Great Dark Spot, a massive storm system that appeared as a large oval-shaped dark region in Neptune's atmosphere, similar in scale to Jupiter's Great Red Spot, but different in structure and behavior. And this storm was not a solid object, but a rotating system of gases moving in organized patterns, with winds circulating around its edges at extremely high speeds. And inside the storm region, the atmosphere appeared darker because of differences in cloud height and composition. And this system was monitored over time as Voyager passed by, showing that the storm was not fixed in place, but slowly shifting and evolving as it interacted with surrounding atmospheric flows. The Great Dark Spot was not the only storm system observed, because smaller bright cloud formations were also seen moving at high speeds across different latitudes, and these clouds appeared to form and dissipate relatively quickly, suggesting a highly active atmosphere where energy was constantly being transferred between different layers. And Voyager data showed that these cloud systems were part of a global circulation pattern, where air rose and fell in large-scale motions, creating dynamic weather structures that operated continuously across the planet's surface. The structure of Neptune's atmosphere also showed clear banding, with alternating regions of faster and slower wind flow. And these bands were not just surface-level features, but extended deeper into the atmosphere, where changes in pressure and temperature created layers of motion that interacted with each other. And this layered structure meant that Neptune's atmosphere was not uniform, but organized into zones that shifted at different speeds, creating shear zones where storms could form and grow, and these interactions helped sustain the large storm systems seen by Voyager during its flyby. As Voyager 2 moved past Neptune, attention turned to its largest moon, Triton, and this object immediately stood out because its orbit was not aligned with the planet's rotation in a normal way. Instead, Triton moved in a retrograde orbit, meaning it travelled around Neptune in the opposite direction of the planet's rotation. And this was a key sign that Triton did not form in place around Neptune, but was likely captured from elsewhere in the solar system, possibly from the Kuiper Belt region, and this capture process would have required complex gravitational interactions that slowed the object enough for it to be pulled into orbit around Neptune rather than continuing on a solar orbit. Triton's surface was one of the most unexpected discoveries of the entire Voyager mission, because instead of showing an old cratered surface like many distant moons, it showed relatively few impact craters, meaning that its surface was geologically young and had been reshaped in the past. And the most striking feature was the presence of smooth plains and layered terrain that suggested internal activity had modified the surface over time, and this activity was not driven by sunlight or external heat, because Triton is extremely cold, but by internal processes that allowed parts of the surface to be renewed in ways that erased older impact marks. One of the most important discoveries on Triton was the detection of active geysers, where dark material was observed erupting from the surface in thin plumes that rose and then drifted downwind. And these plumes were not made of molten rock like volcanic eruptions on Earth or Io, but were instead made of nitrogen gas mixed with dark particles. And this process is known as cryovolcanism, where volatile substances like nitrogen or methane are heated enough to turn into gas and escape through the surface, even in extremely cold environments. And Voyager images captured these plumes rising above the surface, showing that Triton was not a dead frozen body, but an active world where material was still being moved from below the surface into space. The mechanism behind these geysers is linked to seasonal heating and internal energy transfer, where sunlight weakly warms the surface over long periods, causing nitrogen ice to sublimate directly into gas, building pressure beneath the surface until it finds a weak point and escapes in a plume. And once the gas is released, it carries dark material with it, which then falls back onto the surface, creating streaks and patterns that can be seen across Triton's terrain. And this process was captured in action by Voyager, making it one of the first direct observations of active surface change on a distant moon. Triton also showed a thin atmosphere detected through the way sunlight passed through its outer layers during the Voyager flyby. And this atmosphere was extremely sparse compared to Earth or Titan, but still present, consisting mainly of nitrogen with small amounts of methane. And this thin atmosphere was closely linked to surface activity, because the same nitrogen that forms the surface ice can also become gas under slight temperature changes, meaning that the boundary between solid surface and atmosphere was not fixed, but could shift depending on environmental conditions. The surface of Triton also showed large smooth plains that contrasted with more rugged regions, suggesting that parts of the surface had been resurfaced relatively recently, possibly through cryovolcanic flows that spread material across the surface and then froze into place, creating flat regions that covered older terrain. And this resurfacing process indicated that Triton had internal energy sources that kept parts of its surface active even at great distance from the Sun. As Voyager moved farther from Triton and Neptune, it also recorded details of Neptune's magnetic field, and this field was highly unusual because it was not aligned with the planet's rotation axis. Instead, it was tilted at a large angle and also offset from the center of the planet, meaning that the magnetic field did not behave like a simple dipole structure centered inside the planet, but instead existed as a shifted and angled field that created uneven magnetic conditions around Neptune. This irregular magnetic field interacted directly with the solar wind and charged particles in space, creating regions where plasma flowed in complex patterns around the planet, and Voyager instruments recorded how these particles moved through space in ways that changed depending on position and rotation, creating a dynamic environment where magnetic and plasma interactions were constantly shifting. And this behavior suggested that the internal region responsible for generating the magnetic field was not deep and stable like Earth's core, but located in a region where conductive materials were moving in uneven layers, possibly within a shell of fluid material closer to the outer part of the planet. The interaction between Neptune's magnetic field and its environment also affected how charged particles moved around Triton and the surrounding space, creating a region where plasma flows were distorted and redirected by the offset magnetic field, and this made the space environment around Neptune more complex than expected, with interactions occurring between the planet, its moon, and the surrounding space plasma in ways that were not symmetrical or stable over time. The end of planetary exploration. When Voyager 2 finally moved past Neptune, it was no longer in the region of space where planets dominated the view or where close flybys could reveal new surfaces, and instead it entered a part of the solar system where distances between objects grew large, sunlight became extremely weak, and the environment started to shift from planetary influence into a wider space filled mainly with solar wind, charged particles, and slowly thinning material from the Sun. And this moment did not happen with a sudden change or a clear boundary line, because there is no physical wall that marks where the planets end. But instead, it happened gradually as Neptune's influence faded, and the spacecraft began to move into a region where the Sun's presence was still strong, but no longer shaped by nearby planets or moons. And from this point onward, the mission stopped being about visiting worlds and became about measuring the space between those worlds, which had never been directly explored before by any human-made object. As Voyager 2 moved farther away from Neptune, the last images of the planet and its moon Triton slowly shrank into small points of light, and then those points disappeared entirely from the camera's field of view, not because the spacecraft turned away suddenly, but because distance simply stretched everything until even large planets became indistinguishable from background stars. And at this stage, the instruments that had been designed for close planetary imaging were no longer useful for capturing detailed surface features. So the mission naturally shifted into a different mode, where the same spacecraft that once studied volcanoes, storms, rings, and moons now focused on measuring particles, fields, and radiation that filled the space between planetary systems. The instruments on Voyager were not physically changed after launch, but they were gradually reinterpreted and reprogrammed from Earth, so that instead of focusing on reflected light from planets or close atmospheric readings, they began collecting data about the solar wind, magnetic fields, plasma density, and cosmic rays. And this transition was not a simple switch, but a slow adjustment where engineers and scientists carefully selected which sensors to keep active and which to reduce or power down in order to preserve energy. Because the power source on Voyager, a small nuclear system using decaying plutonium, was slowly weakening with time, and every instrument required careful management of limited energy to continue operating in deep space. The solar system in this region is not empty, even though it feels empty when compared to the dense environments near planets, because it is filled with a constant outward flow of charged particles coming from the Sun, known as solar wind. And this wind carries magnetic fields, energetic particles, and traces of material that extend far beyond the orbit of Neptune. And Voyager 2 entered this region as a direct measuring platform, moving through layers of solar wind that changed in density and speed depending on distance and solar activity. And for the first time, instruments could record how this wind behaves far from planetary interference, showing that it does not simply stop or fade evenly, but instead changes structure as it moves outward into deeper space. As Voyager continued its outward journey, the spacecraft began to measure a region where the solar wind starts to slow down and interact more strongly with interstellar material. And this region is not smooth or stable, but filled with turbulence, shifting boundaries, and changing particle densities that form a transition zone between the influence of the Sun and the broader environment of the galaxy. And this zone became the new focus of Voyager's mission. because it marked the first time a human-made object was directly sampling the space, where the Sun's influence begins to weaken and the surrounding galaxy begins to dominate. The instruments that once captured close-up images of Jupiter's moons or Saturn's rings were now used to detect charged particles moving at different speeds and directions. And these particles were not random noise, but structured flows that revealed how energy moves through space on a large scale. And Voyager data showed that the solar wind does not simply fade with distance, but interacts with surrounding material in complex ways, forming boundaries and shock regions where particle speeds change rapidly. And these boundaries are shaped by both the outward pressure of the Sun's particles and the inward pressure of interstellar space pushing back against it. As Voyager moved deeper into this region, it crossed through what is known as the termination shock, a boundary where the solar wind slows down significantly after travelling outward for billions of kilometres. And this slowing is not smooth, because particles collide, compress and heat up as they encounter resistance from the surrounding environment. And Voyager instruments recorded changes in particle density, temperature and magnetic field strength as the spacecraft passed through this region, showing that the boundary between solar influence and interstellar space is not a single line, but a wide, shifting zone where conditions change gradually over distance. Beyond the termination shock lies a region known as the heliosheath, where the solar wind is no longer moving freely outward, but is compressed, turbulent, and mixed with particles from outside the solar system. And Voyager 2 entered this region as part of its continuing journey, recording data that showed strong variations in plasma flow and magnetic field direction. And these variations revealed that the heliosheath is not uniform, but filled with turbulent structures where solar and interstellar forces meet and interact continuously, creating a complex environment that is constantly shifting rather than stable. The spacecraft's instruments measured how the magnetic field carried by the solar wind begins to change direction and strength in this region, because the outward pressure from the Sun is no longer strong enough to maintain a simple structure, and instead the field becomes distorted and folded as it interacts with incoming interstellar magnetic fields, creating regions where field lines are stretched, twisted and compressed. And these changes affect how charged particles move through space, producing a dynamic environment that Voyager continues to sample as it moves outward. At the same time, the spacecraft began to detect changes in cosmic ray intensity, which are high-energy particles coming from outside the solar system. And as Voyager moved farther from the Sun's influence, the level of these cosmic rays increased, showing that the Sun acts as a partial shield against galactic radiation. And once beyond the stronger regions of solar influence, more of these particles begin to enter the local environment, giving direct measurement of how the solar system protects itself from high-energy radiation coming from the galaxy. The instruments on Voyager that were once designed to study planetary atmospheres were also adapted to detect plasma waves, which are oscillations in charged particle environments. And these waves revealed that the space between planets is not empty, but filled with subtle activity, where particles move in coordinated patterns influenced by magnetic fields and solar activity. And these patterns change over time depending on solar output and distance, creating a constantly shifting environment that Voyager continues to record as it moves farther away. As the spacecraft continued outward, communication with Earth became increasingly delayed, and signals that once took minutes now take many hours to arrive, meaning that every command sent to the spacecraft requires long-term planning, and every data transmission requires long waiting periods before results are received. And this delay turned the mission into a slow exchange where information flows in both directions over long time scales, with no immediate feedback or control, only carefully planned sequences of instruction and response. The Deep Space Network on Earth remains the only connection to Voyager, and it tracks the spacecraft using large antennas that must be precisely aligned to receive the extremely weak signals coming from billions of kilometers away. And even small disruptions in alignment or background noise can affect data reception, making the process of communication highly sensitive and dependent on constant monitoring, and as Voyager moves farther away, the signal strength continues to decrease, requiring more powerful and sensitive equipment on Earth just to maintain contact. Heliosphere, boundary science. As Voyager 1 and Voyager 2 moved far beyond the outer planets, the mission entered a region that could no longer be described in terms of planets, moons, or ring systems, because there were no solid bodies nearby to study, and instead the spacecraft was surrounded only by a flowing environment of charged particles coming from the Sun, mixed with weak magnetic fields and sparse interstellar material. And this region is called the heliosphere, which is the vast bubble of space dominated by the solar wind, stretching far beyond the orbit of Neptune and forming a kind of protective region around the solar system where the Sun still controls the movement of particles and magnetic structures, even at extreme distances where sunlight itself is very weak. The heliosphere is not a fixed shell or a hard boundary, and Voyager data showed very clearly that it behaves more like a changing bubble that expands and interacts with outside space. Because the solar wind is not constant, it varies in speed, density, and strength, depending on solar activity. And as it travels outward, it spreads into a larger and larger volume of space, gradually losing strength, but still maintaining enough influence to shape the environment around it. And this means that the heliosphere is always shifting, always expanding and contracting slightly, depending on solar conditions, and always interacting with the surrounding interstellar medium in ways that create complex transition zones rather than simple borders. One of the most important measurements made by Voyager in this region was the way solar wind particle density changes with distance from the Sun. Because near the inner solar system, the solar wind is strong, fast, and dense enough to dominate space conditions, but as it moves outward, it spreads over a larger area and begins to thin out, and Voyager instruments recorded this gradual decrease in density over billions of kilometers, showing that the solar wind does not simply stop at a certain distance, but slowly weakens as it expands. And this weakening is not smooth or uniform because it is affected by solar activity cycles, where bursts of solar energy can temporarily increase particle flow even at great distances, creating fluctuations in the structure of the heliosphere. As Voyager continued outward, it encountered a region where the solar wind begins to slow down significantly due to interaction with interstellar material, and this region is known as the termination shock, where the outward-moving solar wind suddenly slows from supersonic speeds to slower, more turbulent motion as it encounters resistance from the surrounding medium. And this change is not gradual, but happens over a wide boundary region where particles collide, compress, and heat up. And Voyager instruments recorded this transition in real time by measuring sudden changes in particle speed, density, and temperature, showing that space itself can behave like a compressible fluid under large-scale conditions. The termination shock is not a single sharp surface, but a wide region where conditions change rapidly over distance. And Voyager data showed that as the spacecraft passed through this zone, particle behavior became increasingly irregular, with fluctuations in speed and direction that indicated strong turbulence. And this turbulence is created because the outward pressure of the solar wind is no longer strong enough to move freely through space. So it begins to interact more directly with incoming interstellar particles that push back against it, creating a region where two different space environments collide and mix. Beyond the termination shock lies a much larger region called the heliosheath, which is a thick layer of turbulent plasma where the solar wind has slowed down but is still moving outward. And this region is filled with complex interactions between charged particles and magnetic fields. And Voyager instruments recorded how the magnetic field in this region becomes distorted and stretched as it interacts with both solar and interstellar influences, creating a structure that is far from stable or uniform. Because field lines are constantly being bent, twisted, and rearranged as particles move through space. In the heliosheath, the solar wind no longer behaves like a smooth outward flow, but instead becomes a turbulent mixture of slower moving particles, compressed magnetic fields, and incoming interstellar material, and Voyager measurements showed that this region contains irregular waves and fluctuations in plasma density, meaning that the environment is constantly shifting at scales that stretch across millions of kilometers. And these changes are not caused by any single event, but by continuous interaction between outward solar pressure and inward interstellar pressure, creating a dynamic balance that shapes the outer boundary of the solar system. The magnetic field in this region also becomes more complex because it is no longer dominated only by the Sun, and instead it begins to interact with the magnetic field of the galaxy itself. And this interaction causes magnetic field lines to stretch and fold in different directions, creating regions where the direction of the field changes suddenly over distance. And Voyager instruments recorded these changes as shifts in magnetic orientation and strength, showing that the heliosphere is not a simple magnetic bubble, but a layered and distorted structure influenced by multiple forces acting at the same time. As the spacecraft moved further outward, it began to reveal that the shape of the heliosphere itself is not spherical, as was once often assumed, but instead it is stretched out in a way that resembles a comet-like structure, where the front side facing the direction of solar motion through the galaxy is compressed, while the trailing side extends far outward into space, forming a long, tail-like region that stretches behind the Sun as it moves through the interstellar medium. And Voyager data supported this structure by showing differences in particle density and magnetic field strength depending on direction, indicating that the heliosphere is shaped not just by solar wind pressure, but also by the motion of the entire solar system through the galaxy. This asymmetry in shape means that the boundary of the heliosphere is not at a fixed distance in all directions, but varies depending on where you measure it, because in the direction of solar motion, the interstellar medium pushes more strongly against the solar wind, compressing the heliosphere closer to the Sun, while in the opposite direction, the solar wind can extend farther outward, creating an elongated structure that stretches far beyond the planetary region in a tail-like formation that continues into deep space. Voyager measurements also showed that the heliosphere acts as a kind of shield between the solar system and interstellar space, because it reduces the number of high-energy cosmic rays entering the inner solar system, and as the spacecraft moved closer to the outer boundary, the intensity of these cosmic rays began to increase, showing that the Sun's influence acts as a protective layer that changes the radiation environment inside the solar system compared to outside it. And this shielding effect is not constant, but varies depending on solar activity and the structure of the heliospheric boundary. Within the heliosheath, plasma waves and particle interactions become more intense, and Voyager instruments detected fluctuations in these waves that showed how energy moves through this region in irregular patterns, because particles are constantly being accelerated and slowed down by changing magnetic fields. And these interactions create a kind of space weather that is far more diffuse than planetary weather systems, but still structured in measurable ways. And these patterns helped reveal how energy is transferred across vast distances in space environments without solid surfaces or atmospheres. The structure of the heliosphere is maintained by a balance between outward pressure from the solar wind and inward pressure from the interstellar medium. And this balance is not stable in a fixed way, but changes over time depending on solar activity cycles and variations in interstellar conditions. And Voyager data showed that this balance creates shifting boundaries where the position of the outer edge of the heliosphere can move inward or outward depending on these changing forces, making the boundary a dynamic region rather than a fixed shell. As Voyager moved through this region, communication with Earth continued, but became increasingly delayed due to the growing distance, and signals that once took hours now took even longer to travel. And the weak radio transmissions required extremely sensitive receivers on Earth to detect, and even small amounts of background noise could interfere with data reception, making every transmission a careful process of alignment, tracking, and signal enhancement. And this slow exchange of information turned the mission into a long-term observation system rather than a direct exploration mission. The instruments aboard Voyager that once focused on planetary surfaces were now focused entirely on measuring particle flows, magnetic field changes, and plasma behaviour. And this shift in function was not a redesign, but a gradual repurposing of existing tools, where cameras and imaging systems were mostly turned off to save power, while detectors for cosmic rays, magnetic fields, and low-energy particles remained active, allowing the spacecraft to continue collecting meaningful scientific data even in a region where there was no planets or moons to observe. Crossing the heliosphere boundary. Voyager 1, first entry into interstellar space. Voyager 1 was already far beyond any planet when it finally reached the edge of the region controlled by the Sun, and at that point there were no visible landmarks, no clear physical walls, and no obvious change in scenery that could be seen through a camera or a telescope, because space at that distance does not change in a way that human eyes can recognize. Yet the instruments on board began to detect something important happening in the environment around the spacecraft. Something that did not appear suddenly like crossing a line, but showed itself through gradual and measurable changes in the behavior of particles, fields, and radiation. And these changes marked the transition into a region where the Sun's influence begins to weaken, and the surrounding galaxy begins to take control of the environment. The heliosphere at this distance is not a solid boundary, and Voyager data made this very clear, because instead of encountering a wall or a sharp edge, the spacecraft moved through a wide transition zone, where the solar wind, which is a continuous flow of charged particles coming from the Sun, begins to slow down and compress as it meets pressure from the interstellar medium. And this slowing down is not uniform or smooth. It happens in shifts and variations that can be measured through changes in particle speed and density. And as Voyager moved deeper into this region, the instruments recorded a clear change in how particles were moving around the spacecraft, showing that the environment was no longer dominated purely by outward solar flow. One of the key measurements that confirmed this transition was the change in plasma density, because plasma is the charged gas that fills space in the solar wind. And inside the heliosphere, this plasma has a certain expected density based on distance from the Sun. But Voyager 1 began to detect sudden increases in density that did not match the gradual thinning expected in normal solar wind conditions, and these increases showed that the spacecraft had entered a region where solar wind particles were being compressed and slowed down, creating a build-up of density that marked the beginning of a boundary region where solar influence was no longer free-flowing. This change in plasma density did not happen as a single step, but as a series of fluctuations that came and went over time, because the boundary region is not stable. It is affected by changes in solar activity and variations in interstellar pressure. So the spacecraft recorded alternating periods of higher and lower particle density as it moved forward, showing that it was passing through a region of space where two different environments were mixing and competing for control. And this mixing created a complex structure that could only be understood through long-term measurements rather than short observations. As Voyager 1 continued forward, another important change appeared in the magnetic field data, because the magnetic field carried by the solar wind began to shift in direction and structure, and this shift was not random, but followed a clear pattern that indicated the spacecraft was crossing into a region where the Sun's magnetic influence was weakening, and interstellar magnetic fields were becoming more important, and this change in alignment was recorded as a gradual but steady rotation in the direction of the magnetic field lines, showing that the spacecraft was moving into a different magnetic environment that was not fully controlled by the Sun anymore. The magnetic field inside the heliosphere normally follows a structured pattern shaped by the rotation of the Sun and the outward flow of solar wind. But as Voyager moved farther out, this structure became distorted and less predictable, because the outward pressure from the Sun was no longer strong enough to maintain a clean alignment. So the field lines began to bend and shift as they interacted with external pressure from interstellar space. And this created a region where the magnetic field did not point in a single consistent direction, but instead changed gradually over distance, reflecting the transition from solar control to interstellar influence. The heliopause is the region where this transition becomes complete, where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. And Voyager 1 passed through this region not as a sudden event, but as a slow crossing where different instruments detected different signs at different times, because some measurements showed changes earlier while others responded later, which made it clear that the boundary is not a sharp line, but a thick, shifting zone where conditions change over a wide range of distances. And this zone marks the point where the Sun no longer dominates the space environment in the same way it does inside the inner solar system. As Voyager 1 moved through this heliopause region, the plasma environment around it became more complex because instead of a steady outward flow of solar wind, the spacecraft encountered a mix of slowed solar particles and incoming interstellar particles, creating turbulence in the flow that could be measured through sudden changes in particle speed and direction. And these fluctuations showed that the spacecraft was moving through a boundary where two different space environments were directly interacting, creating a region that is neither fully solar nor fully interstellar, but something in between that changes constantly over time. The plasma measurements taken during this crossing showed that particle motion became less uniform and more chaotic, with frequent shifts in density and speed that indicated strong interaction between the remaining solar wind and the surrounding interstellar medium. And this interaction created a compressed region where particles piled up and then spread out again depending on local conditions, making the environment highly variable even over short distances. And Voyager instruments recorded these changes continuously as the spacecraft moved deeper into this transition zone. Another important change came from the direction of particle flow, because inside the heliosphere, particles generally flow outward from the Sun in a consistent direction. But as Voyager 1 crossed into the heliopause region, this flow became disrupted and less organized, and in some measurements, the direction of particle movement began to shift in ways that indicated the influence of external interstellar material pushing back against the solar wind, creating a situation where particle motion was no longer dominated by a single outward direction, but instead reflected a balance between inward and outward forces acting at the same time. The instruments aboard Voyager that measured these changes were originally designed to study planetary environments, but by this stage of the mission, they were being used to study the structure of space itself, and this included detectors for low-energy particles, magnetic fields, and plasma waves, all of which worked together to build a picture of the environment around the spacecraft. And as Voyager moved through the heliopause, these instruments showed a clear shift in the nature of space from a solar-dominated system to one influenced by interstellar conditions. The plasma wave instrument in particular played a key role in detecting changes in density, because when charged particles move through space, they create small oscillations in the surrounding plasma, and these oscillations can be measured as waves. And during the crossing of the heliopause, these waves showed clear changes in frequency and intensity, indicating that the density of the surrounding medium had increased compared to the inner heliosphere. And this provided one of the strongest pieces of evidence that Voyager 1 had entered a new region of space. The shift in magnetic field alignment was especially important because it showed that the spacecraft was no longer fully inside the Sun's magnetic influence, and instead was entering a region where magnetic fields from outside the solar system begin to interact with the remaining solar field, creating a mixed environment where field lines are stretched and reoriented. And this change was gradual rather than sudden, which confirmed that the boundary is not a simple edge, but a layered structure where solar and interstellar forces overlap. As Voyager 1 continued beyond this region, the data consistently showed that the spacecraft had moved into a new environment where the density of particles was higher than expected inside the heliosphere, and where the magnetic field direction no longer matched the pattern shaped by the Sun's rotation. And these combined changes confirmed that the spacecraft had crossed into a region dominated by interstellar space conditions rather than solar wind conditions, marking a major shift in the environment being measured. Even though there was no visible change to mark this transition, the instruments on Voyager 1 provided a continuous record of shifting conditions that showed exactly how the environment changes as one moves from solar influence into interstellar space. And this record revealed that the boundary is not a fixed line, but a thick transition zone filled with changing particle flows, shifting magnetic fields, and fluctuating plasma density, all of which define the region where the Sun's influence finally gives way to the broader environment of the galaxy. Interstellar medium findings. Voyager 1 beyond the solar bubble. After Voyager 1 moved past the heliopause region, the environment around the spacecraft stopped showing signs of dominant solar wind flow, and instead the instruments began to record conditions that came from outside the solar system itself, where the material is not shaped by a single star but exists as a mixture of thin gas, charged particles, magnetic fields, and leftover matter from ancient supernova explosions that slowly fill the space between stars, and this region is called the interstellar medium. And what Voyager found here did not match earlier expectations in terms of density, structure, and particle behavior, because instead of becoming emptier and more uniform as distance increased, the space outside the heliosphere showed measurable structure and higher particle density than expected in several key readings. One of the first clear results came from plasma measurements, because even after crossing into interstellar space, Voyager 1 continued to detect charged particles surrounding the spacecraft. But what changed was the density and stability of these particles, since the plasma outside the heliosphere showed higher density levels than what models had predicted for this region. And instead of a smooth decrease in particle presence, the spacecraft recorded a stable but unexpectedly strong background level of plasma that suggested the local interstellar medium in this region is not extremely thin and empty, but still contains enough charged material to be measured consistently over long distances. This higher than expected plasma density changed the way the outer boundary of the solar system was understood, because it showed that the environment outside the heliosphere is not simply empty space waiting to be filled by solar wind expansion, but a region that already contains its own structured material, and this material interacts directly with the outgoing solar wind, shaping the heliosphere itself by applying pressure back toward the Sun. And this balance between outward solar pressure and inward interstellar pressure becomes more complex when the interstellar medium is denser than predicted, because it means the heliosphere must constantly adjust its shape and size to match external conditions rather than expanding freely into empty space. Voyager instruments measured this plasma environment through multiple sensors that tracked particle density, movement, and energy levels, and the results showed that even in interstellar space, the environment is not uniform, because density levels changed over time and space, indicating that the spacecraft was moving through a region that contains small variations in material distribution, and these variations may come from local turbulence in the interstellar medium or from residual effects of the heliosphere's boundary structure. But in either case, the data showed that interstellar space has measurable structure that can be detected directly rather than assumed to be uniform. Alongside plasma measurements, another major focus of Voyager 1 in this region became the study of low-energy cosmic rays, which are charged particles that move through the galaxy at different speeds and energies, and come from sources outside the solar system, including supernova remnants and other high-energy cosmic events. And inside the heliosphere, many of these particles are partially blocked or deflected by the solar wind and magnetic field. But once Voyager moved beyond the heliopause region, the instruments began to detect changes in both the intensity and composition of these particles, revealing a clearer view of the local galactic radiation environment. The mapping of low-energy cosmic rays showed that the intensity of these particles increased compared to measurements taken inside the heliosphere, because the solar wind no longer acts as a strong barrier. And without this barrier, more particles from the galaxy can enter the local region around the spacecraft. And this increase was not just a simple rise in number, but included changes in the distribution of particle energies, showing that different types of cosmic rays become more detectable once the shielding effect of the heliosphere is removed. Voyager data also showed that these low-energy cosmic rays do not arrive in a completely random pattern, because their intensity changes over time, depending on solar activity cycles and local interstellar conditions, meaning that even outside the heliosphere, the environment is still influenced indirectly by the Sun through long-range magnetic field effects. And this interaction creates a situation where cosmic ray levels are shaped by both local interstellar conditions and distant solar influence at the same time, producing a mixed environment where both sources contribute to the observed radiation levels. The instruments on Voyager that measured these cosmic rays were originally designed to study energetic particles near planets, but in interstellar space, they became tools for mapping the background radiation of the galaxy. And this mapping revealed that low-energy cosmic rays are more present and more stable in this region than expected, showing that the interstellar medium is not only made of thin gas and plasma, but also contains a steady flow of energetic particles that move through space on large scales, creating a background radiation environment that fills the space between stars. Another important result from these measurements was the way particle energies were distributed, because Voyager detected that certain energy ranges of cosmic rays became more visible after crossing into interstellar space, while others remained relatively stable. And this selective increase provided clues about how different particles interact with the heliosphere boundary, since some are blocked or slowed by solar magnetic fields, while others pass through more easily. And this filtering effect helps shape the radiation environment inside the solar system compared to outside it. The transition into interstellar medium conditions also showed that the space outside the heliosphere is not completely separate from solar influence, because even at these distances, changes in solar activity can still affect particle behavior, meaning that the boundary between solar and interstellar space is not a complete separation, but a filtering region where different types of particles are gradually reduced or enhanced depending on their energy and direction. And Voyager measurements captured this gradual transition in real time as it moved farther away from the Sun. As the spacecraft continued its journey, the data collected from plasma and cosmic ray instruments began to form a consistent picture of the interstellar medium as a region that is not empty but structured, where particle density is higher than expected in some areas, and where energy levels remain active due to continuous movement of charged particles across large distances. And this structure suggests that interstellar space is shaped by long-term processes, such as stellar winds from other stars, remnants of past supernovae, and large-scale galactic magnetic fields that extend across vast regions of space. Voyager's observations also showed that the interaction between solar wind remnants and interstellar particles continues even after crossing the heliopause, because traces of solar particles can still be detected far beyond the boundary, gradually mixing with interstellar material over large distances. And this mixing region provides additional evidence that the transition between solar and interstellar space is gradual rather than abrupt, with overlapping layers that extend far beyond the point where the spacecraft first entered interstellar space. The low-energy cosmic ray environment recorded by Voyager 1 also provided a baseline for understanding how radiation behaves outside the protective influence of the Sun, because inside the heliosphere, the solar wind acts as a partial shield that reduces the number of incoming galactic particles, but outside this shield, the full range of cosmic radiation becomes visible. And Voyager measurements confirmed that this exposure is significantly higher in interstellar space compared to regions closer to the Sun, giving direct evidence of how the solar system influences the radiation environment, not just within its planets, but across its entire surrounding bubble. Cosmic ray measurements. Voyager 1 beyond solar shielding. As Voyager 1 moved deeper into interstellar space after passing the heliopause and settling into a region dominated by the interstellar medium, one of the clearest changes recorded by its instruments came from the behavior of cosmic rays, which are high-energy particles moving through the galaxy at near-light speeds, coming from powerful sources such as supernova explosions, pulsars, and energetic processes near distant stars. And what made this stage of the mission especially important was not just the detection of these particles, but the way their intensity and structure changed once the spacecraft moved beyond the region where the Sun's influence had been acting as a partial barrier. Because inside the heliosphere, these particles are constantly filtered, slowed, and deflected by solar wind and magnetic fields. But outside that region, Voyager 1 was finally able to measure them with far less interference, giving a direct view of the galactic radiation environment. The first clear pattern seen in the data was a steady increase in galactic cosmic ray intensity. Because once Voyager 1 crossed into interstellar space, the instruments recorded a higher number of high-energy particle detections over time, and this increase was not a short spike or temporary fluctuation, but a sustained change that remained consistent as the spacecraft continued outward, showing that the heliosphere had been acting as a protective layer that reduced the amount of these particles entering the inner solar system. And without that layer, the spacecraft was now exposed to the full background flow of cosmic radiation present in the galaxy. This increase in cosmic ray intensity was not uniform across all energy levels, because Voyager instruments showed that different particle energies behaved differently once outside the heliosphere, with some energy ranges increasing more noticeably than others. And this selective change revealed how the heliosphere does not block all cosmic rays equally, but instead acts like a filter that reduces certain types of particles more effectively depending on their energy and direction, meaning that the radiation environment inside the solar system is shaped not only by distance from the Sun, but also by how strongly the solar magnetic field interacts with incoming galactic particles. As the spacecraft continued recording data, the pattern of cosmic ray increase became more stable and easier to measure, showing that the environment outside the heliosphere is consistently exposed to higher levels of galactic radiation than inside it, and this confirmed that the Sun's magnetic field and solar wind together form a large-scale shielding system that reduces the penetration of high-energy particles from deep space. And without this system, the inner solar system would experience a very different radiation environment, with much higher exposure to energetic particles from outside sources. Voyager 1's measurements also showed that the increase in galactic cosmic rays was closely connected to changes in the heliosphere boundary region, because even before fully crossing into interstellar space, the spacecraft detected gradual increases in particle intensity as it approached the heliopause, suggesting that the boundary itself plays a major role in controlling how many cosmic rays can enter. And this boundary is not a simple wall, but a wide transition zone where particle filtering begins long before full entry into interstellar space, meaning that cosmic rays are gradually affected rather than suddenly changing at a single point. Once fully beyond the heliopause, Voyager 1 data showed that cosmic ray levels stabilized at a higher baseline, indicating that the spacecraft had entered a region where the solar shielding effect no longer dominates, and instead the particle environment is controlled by the broader galaxy, where cosmic rays travel freely through interstellar space and maintain a relatively steady background level shaped by distant astrophysical sources rather than local solar conditions. This stable increase in cosmic ray intensity provided direct confirmation of the solar shielding effect, because by comparing measurements taken inside the heliosphere with those taken outside it, Voyager clearly showed that the Sun's magnetic field and solar wind reduce the intensity of incoming galactic radiation. And this reduction is not complete, but significant enough to create a measurable difference in particle flux between the inner solar system and interstellar space. And this difference had been predicted before, but never directly measured from outside the heliosphere until Voyager 1 provided continuous data across the boundary region. The solar shielding effect observed by Voyager is not uniform in strength because it depends on solar activity cycles, magnetic field structure, and the shape of the heliosphere itself, meaning that at different times the level of protection offered by the Sun can vary. And Voyager data showed that these variations affect how many cosmic rays reach different parts of the solar system, with some periods showing slightly higher penetration of particles during lower solar activity, and other periods showing stronger shielding when solar wind activity increases. The cosmic ray measurements also revealed that once outside the heliosphere, the spacecraft was no longer affected by sudden drops or fluctuations caused by solar storms or coronal mass ejections. Because inside the heliosphere, these events can temporarily increase or decrease particle levels, depending on how they interact with the solar wind. But beyond the heliopause, these solar-driven variations disappear, leaving a more stable and consistent cosmic ray environment shaped mainly by galactic sources rather than solar activity. Voyager instruments recorded that galactic cosmic rays include a wide range of particle types and energies, and once outside the heliosphere, the distribution of these particles becomes clearer because there is less interference from solar modulation, allowing scientists to directly observe the natural spectrum of cosmic radiation in interstellar space. And this spectrum provides information about distant high-energy events in the galaxy, since these particles carry signatures of the processes that created them, including shock waves from supernova remnants and magnetic acceleration in deep space environments. Another important finding from the cosmic ray data is the way these particles interact with the remaining magnetic fields near the heliosphere boundary. Because even after crossing into interstellar space, Voyager 1 still detected subtle influences from the Sun's magnetic field, showing that the heliosphere does not end abruptly, but gradually fades. And this fading creates a region where both solar and interstellar magnetic effects overlap, allowing some cosmic rays to be slightly deflected or modified even after crossing the boundary, meaning that the transition between solar and galactic environments is extended over a large distance, rather than confined to a single crossing point. The increase in galactic cosmic rays also helped confirm that the heliosphere acts as a dynamic shield rather than a static barrier, because its effectiveness changes over time and depends on both internal solar conditions and external interstellar pressure. And Voyager data showed that this shielding effect shapes the radiation environment throughout the entire solar system, influencing how many high-energy particles reach planets and moons inside the heliosphere compared to the conditions measured outside it. Voyager 2, second confirmation of interstellar space. Voyager 2 crossed the edge of the Sun's influence years after Voyager 1. But what made this moment important was not just that it reached the same general region of space, but that it entered it from a completely different direction, moving along a different path through the outer solar system. And this gave scientists something they never had before, a second set of measurements from a different angle, crossing a boundary that had already been detected once. And this allowed a direct comparison between two separate journeys through the same large-scale structure surrounding the solar system. And what the spacecraft recorded showed that the edge of the solar system is not a simple round shell, but a shifting, uneven structure that behaves differently depending on where and how you cross it. Voyager 2 travelled through the southern part of the heliosphere, while Voyager 1 had moved through the northern region. And this difference in direction meant that each spacecraft passed through slightly different conditions. Because the heliosphere is not symmetrical, it is shaped by the motion of the Sun through the galaxy and by the pressure of interstellar space pushing against it. And this creates regions where the boundary is closer to the Sun in some directions and farther away in others. So when Voyager 2 approached the heliopause, it was entering a region that was not identical to what Voyager 1 had experienced, even though both were crossing the same overall boundary system. As Voyager 2 moved outward, the first clear sign of approaching the boundary came from changes in plasma density, where the instruments began to detect a gradual increase in charged particle density, similar to what Voyager 1 had recorded. But the timing and strength of this increase were different, and this difference gave an important clue that the heliosphere boundary is not uniform in shape, because if it were a simple spherical shell, both spacecraft would have crossed it under identical conditions. But instead, Voyager 2 measured variations in density changes that suggested the boundary was warped and uneven, shaped by external pressure and internal solar wind structure. The plasma data showed that as Voyager 2 approached the heliopause, the solar wind particles slowed down and became compressed, just like in the first crossing. But the rate of change was not identical, and in some regions the slowdown happened more gradually, while in others it appeared more abrupt, and this variation showed that the boundary region contains different layers of interaction, where solar wind and interstellar medium mix in uneven ways. And these layers are not fixed, but shift depending on solar activity and local space conditions. One of the most important confirmations came from the magnetic field measurements, because Voyager 2 recorded a clear change in magnetic field direction as it crossed into interstellar space, and this change matched the general pattern observed by Voyager 1, where the magnetic field stops following the structured spiral pattern created by the Sun's rotation, and instead aligns more closely with the magnetic field of interstellar space. And this shift is one of the strongest indicators that the spacecraft had passed beyond the heliosphere's main influence. However, the exact timing and shape of this magnetic field transition were not identical between the two spacecraft, because Voyager 2 detected a more gradual change in field direction compared to the sharper transition seen by Voyager 1 in some regions. And this difference provided direct evidence that the heliopause is not a smooth, uniform surface, but a wide transition zone, where magnetic fields from the Sun and from interstellar space interact and blend over large distances, creating a complex region where field lines twist, bend, and realign depending on local conditions. The magnetic field data from Voyager 2 also showed that the heliosphere is not evenly shaped, because the strength and direction of the field changed at different distances than expected based on Voyager 1's crossing. And this difference confirmed that the heliosphere is compressed in some regions and stretched in others, forming an irregular shape influenced by the motion of the solar system through the galaxy and the pressure of surrounding interstellar material. And this shape is not static, but constantly adjusted by changes in solar wind output and external space conditions. As Voyager 2 crossed deeper into the boundary region, plasma instruments began to detect changes in particle flow direction, where solar wind particles that were once moving outward in a consistent pattern began to slow, compress, and mix with incoming interstellar particles, and this created a region of turbulence where particle motion became less predictable. And instead of a steady outward flow, the spacecraft recorded a mixture of directions and speeds that showed how two large-scale space environments collide and interact at the edge of the solar system. This plasma behavior matched the general structure observed by Voyager 1, but Voyager 2 provided an important second dataset that confirmed these patterns are not local anomalies, because the same types of changes were observed in a different region of the heliosphere, showing that the boundary structure is consistent in its overall behavior even though local variations exist. And this consistency helped confirm that the heliosphere has a global structure shaped by fundamental interactions between solar wind pressure and interstellar medium resistance. One of the most important differences between the two spacecraft crossings came from the timing and distance at which these changes occurred, because Voyager 2 encountered the boundary at a different distance from the Sun compared to Voyager 1. And this difference showed that the heliosphere is not perfectly symmetrical, but instead has a shape that varies depending on direction, with some regions extending farther into space and others compressed closer to the Sun. And this asymmetry is caused by the motion of the solar system through the galaxy, which creates a kind of pressure front on one side and a stretched tail on the other. The comparison between Voyager 1 and Voyager 2 data also showed that the transition from solar wind to interstellar medium is not a single sharp event, but a process that unfolds over a wide region. Because both spacecraft recorded gradual changes in plasma density, magnetic field direction, and particle flow over extended distances before and after crossing the heliopause, and this showed that the boundary is better described as a layered structure rather than a single surface, with different instruments detecting different parts of the transition at different times. Voyager 2 also confirmed that the interstellar medium outside the heliosphere is not empty or uniform, because after crossing the boundary, the spacecraft continued to measure stable plasma density and magnetic field conditions that were different from inside the heliosphere. And these conditions match the general interstellar environment seen by Voyager 1, confirming that both spacecraft had entered the same large-scale galactic region even though their paths and timing were different. The plasma density measurements from Voyager 2 after crossing the boundary showed levels consistent with interstellar space, similar to Voyager 1's results, but the detailed fluctuations in density were not identical. And this difference revealed that interstellar space itself has variations in structure, meaning that even outside the heliosphere, the environment is not completely uniform, but contains small-scale changes in particle density and flow, possibly caused by local turbulence or variations in the interstellar medium. The magnetic field alignment data from Voyager 2 also supported the conclusion that the spacecraft had fully entered interstellar space, because the field direction became more stable and consistent with the interstellar magnetic field rather than the solar magnetic field, and this alignment provided one of the final confirmations that the heliosphere boundary had been crossed. Since inside the heliosphere, the magnetic field is dominated by the Sun's rotating influence, while outside it becomes influenced by the broader galactic field structure. When comparing Voyager 1 and Voyager 2, one of the most important results was that both spacecraft showed the same overall sequence of changes, starting with gradual plasma density increase, followed by magnetic field shift, followed by turbulence in particle flow, and finally stabilization into interstellar conditions. And this sequence appeared in both missions, even though the timing and distance of each stage differed, which confirmed that the heliopore's crossing follows a consistent physical process even if the exact shape of the boundary varies across space. Voyager 2's data also helped refine the understanding of how the heliosphere interacts with the interstellar medium, because by comparing two different crossing points, scientists could see how local conditions affect the boundary structure, and this comparison showed that the heliosphere reacts to external pressure in a flexible way, adjusting its shape depending on where interstellar material pushes more strongly against it, and this creates a boundary that is not fixed but constantly shaped by the balance of forces between solar wind and galactic environment. The Golden Record, message from Earth. When Voyager 1 and Voyager 2 were already leaving the planetary region behind and moving into deeper space where no human spacecraft had ever travelled before, a very different kind of payload was already attached to both probes, not designed for scientific measurement or engineering tests, but designed to carry a direct sample of Earth itself, stored in a physical format that could survive for billions of years in space if nothing destroyed it. And this object was the Golden Record, a gold-plated phonograph disc attached to the spacecraft body, built not as decoration or symbolism, but as a structured data container meant to represent life, sound, and information from Earth in a form that could be decoded by any future intelligence that might one day encounter it. The Golden Record was not created as a message in a poetic or emotional sense, and it was not designed to express ideas or philosophy, but instead it was constructed as a structured archive of information that could be physically read, decoded, and interpreted using basic scientific principles, because the designers assumed that if any civilization ever found it, they would likely understand physics, chemistry, and signal processing far better than human language, and so the record was built using a format based on analog signal encoding, similar in principle to a phonograph record that stores sound as physical grooves on a rotating disc, except this version was made of gold-plated copper to survive long exposure to radiation, vacuum, and micrometeorite impacts. The physical structure of the record is a circular disc with grooves engraved into its surface, and these grooves contain analog signals that encode both images and sound. And the reason for using analog encoding instead of digital bits is that analog signals can be read without needing exact knowledge of human computer systems, since variations in groove depth and spacing can be translated back into sound waves or image signals if the reader understands how to convert physical motion into electrical signals. And this makes the record more universal in a physical sense, because it relies on basic laws of motion and vibration rather than specific human technology standards. On the surface of the golden record, there are also etched diagrams that show how to decode the information stored inside it. And these diagrams are not symbolic or artistic, but strictly instructional, showing how the record should be played, what speed it should rotate at, and how the signal should be converted into usable data. And these instructions use universal physical references such as the transition of hydrogen atoms, which is considered one of the most basic and common processes in the universe, allowing the creators to define time and measurement in a way that does not depend on human units like seconds or meters, but instead relies on natural constants that should be recognizable anywhere in the galaxy. Inside the golden record are 115 images selected from Earth, encoded in a way that converts visual information into a continuous analog signal, where each image is broken into lines of brightness values that are stored as variations in the groove pattern. And when decoded correctly, these signals reconstruct images showing Earth landscapes, human activities, scientific diagrams, biological structures, and environmental scenes, all chosen to represent a wide range of conditions and life forms on the planet, not as artistic expression, but as data samples of a living world, and each image is arranged in a sequence that allows reconstruction when processed at the correct playback speed. The selection of 115 images was not random, and it was not meant to be comprehensive in a strict scientific sense, because the limitation of storage space on a physical disk forced strict selection criteria, meaning only a small fraction of possible Earth information could be included. And so the images were chosen to represent broad categories such as human anatomy, animal life, plant life, geological structures, weather systems, architecture, and scientific tools. And each category was compressed into a small set of representative samples that could give a structured overview of Earth's physical and biological environment when decoded. Alongside the images, the golden record contains natural sounds from Earth, and these sounds are stored using the same analog groove system, allowing them to be played back as continuous audio waveforms. And these recordings include environmental sounds such as wind, rain, thunder, ocean waves, bird calls, and animal noises, as well as human-generated sounds like footsteps, machinery, and tools. And each sound was selected to represent physical processes or life activity rather than abstract music or performance, focusing on raw acoustic data from natural and human environments. The sound section also includes musical recordings from different cultures and time periods, not as artistic highlights, but as structured examples of human auditory systems and cultural variation in sound production. And these recordings were selected to show differences in rhythm, tone, and instrument use across Earth societies, giving a sampling of how humans generate structured sound patterns using physical instruments, breath, and vocal systems. And these musical pieces were encoded in the same analog format as the natural sounds, allowing them to be reconstructed through playback in space. One of the most important components of the golden record is the collection of human greetings recorded in multiple languages, where spoken phrases such as basic introductions and messages of acknowledgement are recorded in different linguistic systems from around the world. And these recordings are not meant to carry emotional meaning, but instead to demonstrate the existence of multiple human communication systems showing how sound patterns can represent meaning across different phonetic structures, and each greeting is stored as a waveform that captures the full sound of human speech, including pitch, tone, and rhythm. The purpose of including these greetings was not to attempt communication in real time, because the distances involved make direct communication impossible, but instead to provide a sample of how human language sounds in physical form, allowing any future interpreter of the record to analyze the structure of human speech and potentially decode patterns in communication systems if they understand phonetics and sound analysis. And these recordings are placed alongside images and environmental sounds to create a layered dataset of Earth as a functioning biological and technological system. The technical encoding format of the Golden Record is based on analog signal conversion, where both sound and image data are converted into continuous waveforms that are physically engraved into the disk surface, and playback requires a stylus to follow the grooves while the disk rotates at a defined speed, producing electrical signals that can be reconstructed into audio and visual outputs. And the design avoids digital compression or binary encoding, because such systems would require knowledge of human-computer architecture, which may not be universally understood by any future receiver. To define how the record should be played, engineers included a diagram that shows a stylus positioned at the correct angle and speed, along with a reference signal based on hydrogen atom transitions, which act as a universal time reference because hydrogen is the most common element in the universe, and its atomic transition frequency is considered constant across space. And this allows the playback speed of the record to be determined without needing Earth-based time units, ensuring that the data can be reconstructed accurately even if discovered far in the future by a non-human intelligence. The protective design of the Golden Record also plays an important role in its function as a physical time capsule, because it is coated with gold to resist corrosion and radiation damage. And gold is used because it is chemically stable and does not easily react with other elements, which means the disk can survive long exposure to space conditions including vacuum, temperature changes, and cosmic radiation. And the copper base provides structural stability, while the gold layer protects the encoded grooves from degradation over time. The placement of the Golden Record on Voyager was also carefully chosen, attached to the spacecraft body in a position that minimizes exposure to direct impact from micrometeorites while still allowing it to remain part of the spacecraft as it travels through interstellar space, and the record is not powered or active in any electronic sense, meaning it requires no energy to preserve its data, making it fundamentally different from digital storage systems that depend on continuous power or active maintenance. Engineering survival, 50 years in deep space. Voyager 1 and Voyager 2 were never built with the expectation that they would still be operating half a century later, because the original mission design assumed a short operational life focused on flybys of Jupiter and Saturn, with a possible extension to Uranus and Neptune for Voyager 2, and then a gradual shutdown as the spacecraft drifted into deep space. But what actually happened was completely different, because after completing their planetary encounters, both spacecraft continued functioning in an environment that is far more extreme and far more isolated than anything engineers had originally planned for. And the fact that they are still sending back usable scientific data today is a result of careful engineering choices, gradual system degradation management, and extremely efficient use of limited power and communication resources. The most important part of Voyager's survival is the power system, because once a spacecraft leaves the inner solar system, there is no sunlight strong enough to use solar panels effectively. So Voyager was built with radioisotope thermoelectric generators, often called RTGs, which produce electricity through the natural decay of plutonium, where heat generated by radioactive decay is converted into electrical energy using thermocouples. And this system has no moving parts, no fuel burning process, and no external input required, which makes it ideal for long duration missions in deep space where maintenance is impossible. But the trade-off is that the power output slowly decreases over time as the plutonium decays and produces less heat. At launch, the RTGs produce significantly more power than what is available today. And over decades, this output has steadily declined following the predictable decay curve of the radioactive material. And this decline is not sudden, but gradual, meaning that engineers on Earth have had to carefully manage how that power is distributed across spacecraft systems, turning off non-essential instruments one by one to preserve enough energy for the most important scientific tools. And this process has turned Voyager into a carefully optimized system where every watt of energy is accounted for, and every operating instrument must justify its continued use based on scientific value. The communication system has also become one of the most extreme engineering challenges ever managed in space exploration, because Voyager signals travel across billions of kilometers before reaching Earth, and by the time they arrive, they are incredibly weak, far below the level of everyday detectable signals, often measured in fractions of nanowatts, meaning the energy carried by the signal is extremely small. And yet it still contains usable scientific data that can be reconstructed on Earth using large radio antennas and highly sensitive receivers. To maintain contact with Voyager, NASA uses the Deep Space Network, a system of large radio antennas placed around the Earth so that at least one station can always face the spacecraft as the planet rotates. And these antennas have been upgraded multiple times over the decades to improve sensitivity. Because as Voyager moves farther away, the signal becomes weaker and more difficult to distinguish from background noise in space. And without continuous upgrades to amplification, error correction, and signal processing systems, the spacecraft would have become unreadable long ago, even though it is still functioning. The communication delay has also grown dramatically over time, because signals now take many hours to travel one way between Earth and Voyager, meaning that any command sent to the spacecraft requires long planning cycles, and there is no possibility of real-time control. Instead, every instruction is prepared in advance and sent as part of carefully designed sequences that account for time delays, signal loss, and the limited energy available on board. And this creates a situation where Voyager operates almost independently, following instructions that were sent long before any result can be confirmed. Inside the spacecraft, hardware degradation has become a major factor in long-term survival, because exposure to cosmic radiation over decades slowly affects electronic components, causing bit flips in memory systems, weakening circuit performance, and occasionally disrupting instrument readings. And while Voyager was built with redundancy systems that allow backup components to take over when primary systems fail, the gradual accumulation of radiation damage means that engineers must constantly monitor system performance and adjust operations to avoid critical failures. Memory systems on Voyager are extremely limited by modern standards, and they store commands and instrument instructions in very small capacities. Yet they continue to function because they were designed with extreme simplicity and robustness, using fixed instruction sets that can survive radiation exposure better than complex modern systems. And this simplicity has helped the spacecraft remain operational even after decades of continuous exposure to deep space conditions that include high energy particles and temperature extremes. Software redundancy is another key factor in Voyager's survival, because the onboard systems include multiple layers of fallback instructions that allow the spacecraft to continue operating even if certain parts of the software fail or become corrupted. And this redundancy ensures that critical functions like communication, orientation, and instrument control can still operate even under degraded conditions. And this has been essential in extending the mission far beyond its original design life. The current status of Voyager 1 and Voyager 2 reflects this gradual process of controlled reduction in active systems, where non-essential instruments have been shut down over time to preserve power for the most important scientific tools. And despite this reduction, both spacecraft are still active and continue to send back data, with key instruments such as magnetometers and cosmic ray detectors still functioning, allowing scientists to continue measuring the environment of interstellar space and the outer heliosphere. Voyager 1 remains the farthest human-made object from Earth, travelling through interstellar space beyond the influence of the solar wind, while Voyager 2 follows a slightly different path, but is also now in interstellar space, making both spacecraft the only human objects operating beyond the heliosphere. And this distance means that they are now sampling regions of space that no other spacecraft has ever reached, providing unique data that cannot be obtained from Earth-based observations or other missions. Even though many instruments have been shut down, the remaining operational systems continue to provide valuable scientific data, especially the magnetometer, which measures magnetic field strength and direction, and cosmic ray detectors, which measure high-energy particles coming from both the Sun and the galaxy. And these instruments have become the core scientific tools of the extended mission, focusing entirely on measuring the structure of interstellar space and the outer boundary of the solar system. The expected operational limits of Voyager are projected to fall in the mid-2030s, when the remaining power from the RTGs will no longer be sufficient to support even the most essential instruments, and at that point, communication and data collection will gradually cease, not due to mechanical failure, but due to the natural decay of the power source. And as power declines further, systems will be shut down one by one until the spacecraft can no longer transmit data back to Earth. Even as the mission approaches its final operational phase, its scientific impact remains extremely large, because Voyager fundamentally redefined the boundary of the solar system by showing that the edge is not a fixed line, but a dynamic region shaped by the interaction between solar wind and interstellar medium. And this discovery came directly from real measurements taken by the spacecraft as it crossed through the heliopause and entered interstellar space. Voyager also provided the first direct sampling of the interstellar medium, giving real data about particle density, magnetic field structure, and cosmic ray behavior outside the heliosphere, which had never been measured in place before. And this data confirmed that interstellar space is not empty, but contains structured material that interacts with the solar system on large scales, shaping the environment around it in ways that were only partially understood before the mission. The planetary science impact of Voyager is equally significant, because during its early mission phases, it transformed understanding of the outer planets, starting with the discovery of active volcanism on Io, which showed that a moon could have ongoing geological activity driven by tidal heating. And this finding changed assumptions about how heat sources operate in planetary systems, demonstrating that internal heating can drive surface activity even far from the Sun. Voyager also contributed to the foundation of the Europa Ocean hypothesis by revealing a cracked and resurfaced ice surface that suggested movement beneath the surface layer, which later became a key piece of evidence for the possibility of a subsurface ocean. And this idea reshaped planetary science by expanding the range of environments where liquid water might exist beyond Earth. At Neptune, Voyager measured extremely high wind speeds in the atmosphere, setting records for the fastest winds observed in the solar system. And these measurements showed that energy processes in distant planets can produce extreme atmospheric motion even with very low sunlight input, suggesting that internal heat and atmospheric dynamics play a major role in shaping planetary weather systems. From an engineering perspective, Voyager has become a benchmark for long-duration spacecraft design, because no other mission has operated for this length of time in such extreme conditions. And the combination of RTG power systems, radiation-hardened electronics, redundant software design, and carefully managed communication systems has demonstrated how spacecraft can be built to survive far beyond their expected lifespan, providing a working model for future deep space missions that may travel even farther into interstellar space.